opportunity to speak before you today. It's a privilege to be speaking on this prestigious platform for the faculty development program that has been nicely organized at YCCE. My name is Shashwat, as was kindly introduced by Professor Pawar. I am currently a postdoctoral research scholar with the Department of Materials Science and Engineering at North Carolina State University. So as a material scientist, today I would like to give you all a flavor of how developing cutting edge technology uh, in semiconductors involves engineering the semiconductor materials at atomic scales. Yes, you heard me right. You have to engineer semiconductor materials at atomic scales to realize cutting edge technologies that we witness day in and day out. So, speaking of technology, isn't it amazing that we can communicate seamlessly over the Zoom platform while being 15,000 kilometers away? So, I take that most of the organizers are based in Nagpur, which is the geographic center of India. And I'm currently in a city called Raleigh, which is the capital of the state of North Carolina. And I am based off the east coast of the US. So it's about 15,000 kilometers between us. So we are on the opposite sides of the globe, but here we are communicating seamlessly with a lag of only a few milliseconds. Uh, so this is all thanks to the revolution of communication technology. All right, so I would like to give a brief background of my educational journey so far, or rather my academic training. So it all started in 2010 when I decided to pursue my Bachelor of Technology degree from VNIT, which is Vishweshwarya National Institute of Technology, Nagpur. And my major was in metallurgical and materials engineering there. During my PhD, I was fortunate to spend my summers at these two beautiful laboratories. The one on the top is the Bhabha Atomic Research Center in Mumbai, and the one on the bottom right is the National Metallurgical Laboratory in Jamshedpur. So it's really these two experiences uh, where my research inclination stems from. And these experiences really paved my way to continuing my academic journey to go on to pursue my PhD at SENS at Indian Institute of Science. The previous speaker very nicely discussed things at IISc, how things work at SENS. So I would not get to go into a great detail. Already, I think everyone is aware how great Sense is. But so this was right after my thesis defense at Sense in 2019 with my parents and with my advisors, Professor Nath, who addressed this FDP on Tuesday, I reckon, and Professor Srinivasan Raghavan, uh, who happens to be my primary supervisor for my PhD. And I was also uh, lucky to learn a lot from Professor Muralidharan, who happens to be the ex-director of a DRDO lab in Delhi, which is the Solid State Physics Laboratory. All right, so a little bit about SENSE, and as you must know, SENSE stands for Center for Nanoscience and Engineering. So before I go into what all research happens at SENSE, let's ask everyone a simple question. How small is a nanometer? So let's try to put our thoughts in the chat box. So let's allow us 15 seconds, and I would like to hear from you. What do you believe? How small is a nanometer? All right, I don't see any comments yet. So let me move forward. As most of you must have guessed it right, nanometer is 10 to the minus 9 meters. So if you put 9 zeros after the decimal point, that's what a nanometer means. So to give a physical uh, uh, relevance, let's talk about red blood cells that most of us are aware of. So a red blood cell is still about 7,000 nanometers wide. A human hair is about 50,000 to 1 lakh nanometers thick. So a nanometer is 10 or a 50,000th part of the thickness of a human hair. Or another physical dimension that I would like to highlight is that your fingernails grow at about a nanometer per second. So, so if I were to compare a nanometer to a tennis ball, then it is what is to tennis ball is what the tennis ball is to the earth. So if the tennis ball is a 10 to the 10 of a nanometer, then the Earth is 10 to the 100 of a nanometer. So that's how small a nanometer is. So a nanometer would also constitute of about 4 molecules if you were to space them next to each other. So it is that small. So now you must be wondering, can anyone really research at such small scales? And this is something that I'm going to discuss in this presentation as to how you go about engineering at such nanoscales. So let's look at a common example that we must have known. So if you go to 1990s, this is how a transistor would look like. And this is a processor. We have about 3,500 transistors packed in this one processor. But now if you look at an i7 chip, then it has billions of transistors spaced in a single processor chip. So it's indeed amazing that all the cell phones that we carry, everybody carries in this day and age, packs billions of such transistors. And all of these transistors have a technology node of only a couple of nanometers in size. So we have scaled down things to this extent that now we are realizing transistors that are only few nanometers wide. So that brings me to all the research that happens in sense. So with this background, I very much believe, and it would be fair to say that we live in an electronics world. We interact with several electronic devices day in and day out, and at the heart of every electronic system is a carefully optimized material system that enables any electronic technology. So, so before developing any electronics, you have to first develop the material system that lets you now put your electronic devices on top of. So these two fields, although seem like they should go hand in hand, but often this is not the case. So growing up as a material scientist, I always wanted to know more about electronics and understand how electron devices work at such small scales. And I took this opportunity to work at the intersection of these two fields and try to expand my expertise in electronics as well to eventually go on to make significant progress in the research I could do. So apart from electronics and materials, this center also works on micro and nano electromechanical systems. So these are used in sensors, accelerometers, actuators that form critical components in a range of products, including cars, cell phones, inkjet printers, to name a few. So it's a very important field of research. The next field of research, in sense, is microfluidics. where we really understand how the behavior of fluids in tiny volumes can be very different than that of the bulk. And this is because for such tiny volume of liquids, the fluid surface and surface forces come into play and try to dominate the behavior. And this research area finds a range of healthcare applications such as DNA sequencing, biosensing, as well as applications such as self-cleaning super hydrophobic surfaces. So you are soon going to see such super hydrophobic surfaces on your sunglasses, on the windshield of your cars, that would allow you to have a clean surface all the time and not even be needing the use of a wiper. So these technologies are of great significance as well. So the next research topic is nanobiotechnology, where the central theme is to use nanoscale devices and systems to develop novel diagnostic and therapeutic solutions for biomedical applications. So these can include targeted drug delivery inside the human body, and so on. So another very cool research domain that the center works on. Uh, then we have neuroelectronics, which is a rather new research domain that broadly relates to interfacing the neurons in the nervous system uh, to electronic devices. So one of the applications is trying to understand how a human brain works and then develop electronic systems that mimics the functioning of a human brain. So this is a rather new research domain. Then we have research in photonics, which concerns the science of light, including the generation, processing, transmission, and detection of light and its interaction with matter at various length scales. And the applications here include optical sensing, integrated optics, lasers, and optical communications. And very importantly, we also have a lot of technology development because at Sense, as the previous speaker pointed out, the key development uh, technologies that the center works on. Uh, uh, so these are used to create startups. Uh, and the previous speaker already talked about a range of startups that have stemmed from the center. And it's amazing that was established only 10 years back, and we already see about 8 to 10 startups coming from the center. So I was very fortunate to spend 5 years here as a PhD student, and although I worked on electronics and materials, I could learn so much in the other domains as well. So I would say it was a long but very exciting journey from somebody who did metallurgy, where uh, uh, the scale at which you do things is rather large, such as iron making and steel making in blast furnaces, which is very huge in size. But then I went on to become someone who does nanomaterials for nanoelectronics, where now the size of the entire packaged device is smaller than the width of a finger. So it was a very exciting transition from somebody who did only metallurgy and material science to somebody who does both of these worlds with uh, sense. It was not only a lot of learning, but a lot of fun as well. During my PhD, I was fortunate to improve my chess skills. I played a lot of table tennis, cricket. I could attend a lot of conferences. So here's me with the Eiffel Tower. This is the New York skyline. This is Singapore Zoo. And we used to have a lot of lab outings that I thoroughly enjoyed as well. All right. So that paved my way to North Carolina State University, where I'm currently at as a postdoctoral research scholar. So this is our Centennial campus. It's a very beautiful campus, and my office is very close to the main library, that overlooks this beautiful lake that I get to hike every other day. Um, so this library is state of the art. Uh, it actually employs robotic arms to deliver a book to you within 5 minutes. So I think it's a very efficient use of space, and thanks are due to the robotics technology that enables this. So you can pack many more number of books in a smaller space if you were to go about making every library such as this. So this is one of my favorite places to go to. Uh, the library, which has very nice indoors, but also amazing outdoors, and you can work in the balcony overlooking this beautiful lake. So it's an experience in itself. And if you happen to be in this part of the world, please touch base with me, and I'll like to show you the campus. All right, so this brings me to the theme of my research of what I work on. So as I mentioned, my aim is to act as a nexus between these two important fields of material science and semiconductor electronics. So to show you what I work and how I go about doing things, I show a tetrahedron here. So it all starts with an application in mind. For instance, if I want to develop a semiconductor power device, I have an a priori knowledge of what material would suit the best for such applications. So I start with that idea in mind and go about processing and synthesizing the material. Uh, After that, while processing, I try to understand how the microstructure or the structure of the material is going to evolve. Because as I'll be showing in the next slide, structure of the material has implications on the properties that the material is going to the material is going to possess. So we tune the microstructure to get to desired properties, and then we tune the properties to get to the desired device performance. So that's how the workflow works. And at the heart of all this is characterization that helps us navigate this path. So between processing and microstructure, we have a range of characterizations that allow us to understand if we are um, doing things the right way or not. And then between structure optimization and property optimization, also you can have a range of characterization techniques that really help you understand and navigate this workflow. So let's look at how the crystal structure changes the properties of the material. So it's a very basic slide, but I wanted to discuss this right at the start. Uh, so, so, so the material properties are really a complex function of the chemistry involved. So this would be the number of components and their amounts. It depends on the type of bonding, whether the bonding involved is ionic in nature, or is it metallic in nature, or is it covalent in nature. So ionic bond would be, for instance, sodium chloride, where you have constituent atoms with a large electronegativity difference. So you have almost a charge transfer between the two constituent atoms. So that would make an ionic bond. Similarly, you have metallic bond, as the name suggests. It's common in metals. You have covalent bond where the electron is shared between the two atoms about equally. And then most of the bonds have a mixed nature. And the bonding has implications on how the material is going to synthesize, how the properties are going to turn out. So the type of bonding is a very crucial information that one must be aware of while designing a material for a specific application. The properties can also be a sensitive function of external variables, for instance, temperature. Uh, so if we take an example of a superconductor, then it has a reasonably high resistivity at higher temperatures, but once you go below a critical temperature, that's when the magic starts and the material loses all the resistance and it behaves like a perfect conductor while giving very less resistance. So some material properties can be a sensitive function of temperature. Similarly, we can have materials that are responsive to pressure. For instance, the touchscreen panels on our mobile phones are based out of such materials that respond to pressure, where the mechanical energy is converted into electrical energy, and that's how our cell phones understand that we are trying to type in a specific thing. And similarly, we can have materials respond very differently in the presence of electric fields. Um, then the material properties also depend on the type of structure involved. So type of stacking you have when you make a crystal, is it body-centered cubic? Is it face-centered cubic? Or is it hexagonally closed packed? So it's all high school chemistry or first year undergrad chemistry that I'm showing here, and this governs how the material is going to behave. Last but not the least, the most important thing in my research is understanding how a material microstructure changes the properties of the material. So by microstructure, I am referring to defects in the material that can be present at levels as small as part per million. So by part per million, I mean that you can only have one defect in a million atoms, and still it can alter the properties of the material to a significant extent. So let's look at this schematic, and I would like you to type in uh, how how many number of defects can you point out in this schematic. So let's allow us about 30 seconds to look at the arrangement of atoms in this schematic, and let's try to answer how many defects can you uh, visualize here. So just type in a number of defects, let's say one defect or two defects or 10 defects. So how many defects can you point out in this schematic? So let's just type in our answers. Okay, so we have one. Um, we have one comment which states that there's one defect. Okay, can you? Okay, so we have 8 and we have 6. All right, so I'm happy with those responses. So let's try to figure out how many defects are we dealing with in this schematic. So one of the most common defects that one can observe is known as a substitutional defect. So here we can see that a foreign atom is now trying to replace a constituent atom from its lattice site. And when it does that, you can see that now all the bonding around this defect has altered. So essentially, we can define a defect as uh, a feature that disrupts the translational periodicity of the crystal. By that, I mean that if you look away from this defect, then the bonds are arranged in a nice periodic manner. But when you move in close to the defect, then you realize that the bonds now get stretched or compressed, and basically it's disrupting the translational periodicity of the crystal. So remember, I pointed out that the bonding in the material has important implications on the properties. So this is one of such consequences where you are altering the bonding environment around the defect, and that changes the properties of the material in a drastic fashion. I'll be explaining that in the next slide. Then we have another defect here. This is called a vacancy because one of the constituent atoms has now left its site, and the site is now vacant, and we call this vacancy. So basically, to create such vacancy, one would have to remove these 4 bonds with the adjacent atoms. And you can again see that the bonding configuration now gets altered significantly as soon as you remove one atom. So as I'll be showing in the next slides, if even if you remove one in a million atoms, so 1 in 10 to the 6 atoms, still you are going to change the properties of the material significantly. Then you can have a defect called as an interstitial defect, where you have the constituent atom incorporated in the lattice, but it is not at the exact lattice site. So you can see that it incorporates in between these 4 atoms. And this can be termed as interstitial defect. We can also have the foreign atom occupying this site. And we can have cluster of these foreign atoms coming together to form a defect complex. So all of these defects can be termed as zero-dimensional defects because they are only one point. So it's zero dimension. But now, if you turn your attention to this defect here, this is an example of a one-dimensional defect. So what this looks like is that you have removed a half plane of atoms from this area, right? And in doing so, you create a one-dimensional defect in the crystal. It's called as dislocation because it seems like you have dislocated the crystal halfway by creating this defect. And you can see that it has also changed the bonding around it significantly. And as I'll be showing later, that such defects also change the properties of the semiconductor material drastically. So let's look at how doping works in semiconductors. So this is how we make the semiconductors work, and this is how the transistors are realized. So silicon is the most explored semiconductor. It's an elemental semiconductor, group 4 semiconductor. So to make it n-type, by n-type, I mean that it should have an excess electron. You can dope it with a group 5 element. So in this case, let's say we are doping it with phosphorus. So what phosphorus does is that it brings along an extra electron to the lattice, which is very weakly bound to the lattice. So you can give it very small energy and it can now free out that electron and it's now available for conduction. So that's how you make n-type semiconductors. In p-type, what you do is instead of group 5, you now substitute with a group 3 element, boron in this case. So what boron brings along is a deficiency of an electron. So you see here that now your lattice has one deficient electron. And now this deficiency can also be loosely bound, and if you give it sufficient energy, then you can have an electron occupy this hole, and in this process you are creating a hole at the original site from where the electron originated, and that's how you can transport the hole inside the semiconductor. So that's how you make p-type semiconductors. Now let's see how these how the resistivity of the silicon semiconductor changes as you increase the dopant concentration. So let's say that we are in a rather pristine material with only 10 to the 12 dopants. So in a 1 centimeter cube volume, typically the number of atoms in the silicon semiconductor would be 10 to the 23 atoms. So when you are doping 10 to the 12 atoms, then you are doping it with a rather low concentration. But you soon realize that as you increase the doping concentration, you are changing the resistivity by orders of magnitude. So resistivity is the tendency of the material to conduct current in a given unit area. So you see that by incorporating, let's say 10 to the 17 defects, which is part per million, you are changing the resistance of the material by 5 orders of magnitude. So this is how uh, the defects play a role at such small scales. So it's very counterintuitive, but it is how it works. That if you have even a part per million of defects, then it can really change the behavior of a material. In this case, the resistivity, and this is what allows us to dope the silicon semiconductor. And this is how a transistor is realized out of the silicon semiconductor system. So let's look at another way how point defects can change properties. In this case, let's look at optical properties. So this is how sapphire wafers look like. So these are wafers that we routinely used for our devices during our PhD, and I still use them. So this is how a defect-free sapphire would look like. It is transparent to all the visible radiation that we are sensitive to. Now to the right, I have some crystals. I can tell that these are all sapphire. But now, can you post it in the chat box as to why do sapphire crystals have different colors here? All of these are sapphire. So let's try to understand why these have different colors. So can someone try to attempt this question? So we have sapphire crystals here, and I want you to answer why they look so different. All right. So the answer is that the sapphire crystals have various point defects. So depending on the point defect, you can have a different color embedded in the crystal. So for instance, if you have iron in parts per million, it would give out a red color. If you have copper, it would give out orange color. So for every kind of defect, even in parts per million, you can have very nice, beautiful sapphire crystals. So I really think that it's the defects in the materials that make materials beautiful. And I'm not the only one. These people also share the same opinion as me. Here, for instance, Sir Charles Frank relates people to crystals, and he believes that it's the defects in people that make them interesting. Uh, here, William Morgan says that perfection has one grave defect. It is apt to be dull. So what he's trying to refer to is that to get a perfect crystal, there's only one way to get a perfect crystal, but you can have a million ways in which the crystal is defective. And it's that variety that makes these crystals so beautiful. So with that, let me try to show you the materials that I work on. So the first material system that I work on is three nitrides. So basically, it's the group 3A elements, aluminum, gallium, and indium, and we bond them to nitrogen. Remember, I mentioned that the bonding in these materials can have important implications on the properties. So the way these elements bond with nitrogen, they make semiconductors with a large band gap. By band gap, I mean the energy needed to free out an electron to a free state where now it can be conducted. So the more the band gap, more would be the excitation energy you would need to free out an electron from the valence band. So the first material system that I work with is three nitrides. The second material system that I work with is called as transition metal dichalcogenides. So the material I work on is molybdenum amongst all these transition metals, and we bond them to two sulfur atoms, making it MOS2. So I work on these materials as well, and I also work on silicon that I showed in the previous slide, which is an elemental semiconductor, but I have worked on nanowires made out of this, as I'll be showing in the next slide. So essentially, depending on the scale or the thickness of these three nitrides, you can have two-dimensional or three-dimensional materials that you are going to work with. But 2D materials, that is MOS2, is a layered material where now you only have two dimensions of interest, the length and width of these crystals, because thickness is only one atomic layer thick. So that's how thin these materials are. That's why I refer to them as 2D materials. We then have silicon nanowires, as the name suggests. These are wires, but its cross section is in nanometer scale. And that's why we refer to these materials as one-dimensional materials. So I think in the interest of time, I'm going to speak the most about is 3A nitrides and the applications that these materials enable. Uh, so broadly speaking, I work on power electronics and optoelectronics, uh, where power electronics is the application of electronics to the control and conversion of electric power. So I'm going to acquaint you about power electronics in the next 10 or 15 slides. Uh, I also work on optoelectronics, which is the study and application of electronic devices and systems that find, detect, and control light. So I'm also going to touch upon optoelectronics applications that these materials enable. Uh, so let's first talk about power electronics. So here I show you the evolution of power semiconductor devices. So it all started in 1948 when the transistor was invented, and that was driven by germanium. Germanium was the workhorse material for several decades. We saw the invention of thyristors, and then in 1965, silicon was invented, as in it was demonstrated to have good semiconducting capability, and that's what led to the development of power bipolar transistors, power MOSFETs, insulated gate bipolar transistors, and photothyristors. Then came the advent of gallium arsenide based radio frequency devices. And then it was only in the 20th century that we started seeing silicon carbide and gallium nitride based devices. So we saw gallium nitride field effect transistors in 2004, and in 2009 we saw the first gallium nitride integrated circuit. So gallium nitride is the most promising semiconductor for power devices at the moment, and the promise is summarized in this slide. So for any power electronic device, what is important is that in its on state, the power device should be able to conduct a large amount of current at low application voltage, which means that it should have a low on resistance. And in its off state, is supposed to hold on to a large breakdown voltage. So that comes in the numerator. So essentially, what we want in this graph is that we want low on resistance and high breakdown voltage. So we want to be on the bottom right. And as we can see, that these depend eventually on the mobility of electron. The mobility is the ease with which electrons can flow in the semiconductor. And then you have a dependence on the critical field that now that now is a representation of how much field can the semiconductor material support. So we see that the mobility for gallium nitride is has a reasonably higher number. It's better than silicon, slightly worse than gallium arsenide. But what comes in favor of gallium nitride is its critical field strength, which is 3 megavolt per centimeter. So it's a large field, and gallium nitride can support such large fields without breaking down. And this number is higher than all these other semiconductors that I have benchmarked gallium nitride against. And this is what lets gallium nitride be very efficient. So when we make power devices based out of gallium nitride, uh, the better figure of merit lets gallium nitride devices operate at higher efficiency. The low on resistance means that you have low resistive losses, which allows for a cooler operation. And then since these devices are so efficient, you can pack many devices in the same footprint, thereby reducing the size of the packaged device that you want to enable a specific application. So that's where gallium nitride finds promise. And if we now look at the applications of gallium nitride power transistors, then depending on the rating, voltage rating, you can have a range of applications from power supplies to automotive electronics. Then at higher voltages, you have factory automation, similar to automation showed by the previous speaker. Then we have motor control and traction motors at higher voltages, and then we have high voltage DC to DC conversion. So if you look at electric vehicles and hybrid electric vehicles, gallium nitride transistors enable a range of transistors in these automobiles, starting from the low voltage audio systems that require less than 10 volts of voltage to we have traction inverters now which are used to sequester the mechanical frictional energy when we apply brakes, and it converts it into electrical energy that now charges the battery in your electric vehicles. You have DC to DC converter, and this is the step up converter where it is increasing the voltage from the rating of the battery to delivering a higher voltage to the rotary motor that is now working on moving this car forward. Then we have wireless phone charging, we have onboard chargers, a range of sensors, and then as has been the talk of a couple of weeks, the Tesla is working extensively on enabling wireless car charging, and gallium nitride is going to play a big role in enabling this technology as well. So if you look at the more of market that most of us are more aware about, it is the fast charging market. So all of us know about the fast mobile charging technology that we saw in the Oppo and Realme phones back in 2018. So this was enabled using gallium nitride. So early on, we mostly had a slow chargers that were based out of silicon because silicon is cost effective and it works well in this wattage range. But as we move from 30 to 100 watt, there is a competition between silicon and gallium nitride, with gallium nitride being more efficient but silicon being more cost effective. There is a trade-off between the two, and we have a competition between the two. But the Chinese companies are favoring GaN, and they believe that when we go to more than 100 watt charging, it's going to be gallium nitride's market. So if we see the forecast, then even with only the Chinese companies using GaN for their fast charging, the market is expected to be at $350 million. And with the best case that Apple, Samsung, Huawei also join forces with these Chinese companies and adopts gallium nitride for their fast charging applications, then the market is expected to be twofold of the nominal case and at about $750 million. So overall, the market size is soon expected to reach $1 million just for the fast charging applications. To summarize, we spoke about how gallium nitride enables a range of applications depending on the wattage that the device needs. For instance, at low wattage, we have the wall plug adapters. Then we have fast charging adapters for our cell phones and laptops. Then we have servo motor drives. Then we move to electric two-wheelers. Then we have telecommunication and UPS. Then we have the DC to DC converters, onboard chargers, and at higher wattages, we have the drivetrain inverters. So if we look at the roadmap of how gallium nitride power devices are going to look like in the next decade or so, then we notice that it only started in 2010, but the market is picking up nicely, and it's expected to proliferate as we move to the later part of this decade. So in 2017, gallium nitride was only used in low volume in high-end photovoltaic inverters. But in 2020, we saw that most of the cell phone chargers are now adopting gallium nitride technology. In 2024, many more companies uh, uh, are getting involved with gallium nitride technology for electric vehicles, hybrid electric vehicles, for DC-DC conversion, and also in data centers. So we see that the market is starting to proliferate now. And then eventually we expect gallium nitride to play a big role in the industrial market as well. And then we see that it crosses $1 billion market in 2030. So right now, it's mostly consumer electronics that gallium nitride has enabled, but soon we are going to see automotive, and eventually we are going to see a lot of industrial market for gallium nitride. Uh, so if we again talk about the revenue the gallium nitride is expected to generate, then we see that a major chunk is from consumer electronics at about 13 million in 2020. Uh, Out of the total 46 million. But if we fast forward to 2026, then we expect the consumer electronics still to dominate, but all these other areas are also going to grow with an average compounded annual growth rate of about 70%. So these are going to be industrial applications, telecommunication, data communication, automotive, defense and aerospace sector, energy, and other applications as well. So I spoke about all the power electronic market that gallium nitride has, but a significantly bigger market is the radio frequency market, which is already at 900 million, so about close to $1 billion market already. While it was mainly used in defense and in enabling 5G telecommunication. So this is where gallium nitride is helping us revolutionize towards 5G by enabling efficient base stations. So base stations are the ones that enable these high frequency antennas, and gallium nitride is enabling all of this technology. But it's expected that we also develop a lot of satellite communication based out of our gallium nitride radio frequency devices in 2026. So the market is expected to grow to $2.5 billion, and then even more in 2030, where it is expected that our handsets are also going to uh, uh, get improved with the gallium nitride technology. So this was the radio frequency market, and before this, I talked about the power electronics market. Now let's look at how gallium nitride enables optoelectronics. So if you remember, I spoke about power electronics in the start, and then I talked about optoelectronics. So this is one of those unique semiconductors uh, that has capabilities in many applications. As the previous speaker pointed out, that gallium nitride enabled the blue light emitting diodes or the white light emitting diodes that we are used to seeing. So these are ubiquitous now, but as I'll be showing later as to why this was a big achievement and how the material system needed about 30 years of research before we could make efficient light emitting diodes. And that was the reason why these three Japanese scientists uh, rightfully received the Nobel Prize in Physics for the development of blue light emitting diodes. So this was based out of indium gallium nitride material. So as you move to the left, you move into the infrared region of the electromagnetic spectrum. But if you move to the right, when you are alloying gallium and aluminum in the alloy, then you move towards ultraviolet and deep ultraviolet regions of the electromagnetic spectrum. And this is where things get very difficult, as I'll be uh, discussing in the next few slides. So in the AlGaN material system, if you have 0% aluminum that is gallium nitride, it enables 3.4 electron volts of band gap, which corresponds to uh, 360 nanometers of wavelength. Uh, and when you move towards aluminum nitride, that enables a much higher band gap, which is 6.1 electron volts. And then it corresponds to about 200 nanometers of wavelength. So by tuning this aluminum mole fraction, you can enable an entire range of UVA, B, and C radiations. And again, as the previous speaker pointed out, that if we were to look at the UV spectrum coming out of the sun, then most of it consists of UVA, a small fraction of UVB, and a negligible UVC. And this is because the ozone layer above the Earth's surface absorbs all the radiation in the UVC. So this region of the electromagnetic spectrum is termed as solar blind because it is free from the UVC background. And if we make detectors in in this wavelength regime, then we can go about detecting missile plumes, for instance. So if you imagine detecting a missile from, if you were to detect the missile from the surface of the Earth, and if we are trying to detect it against the sky, then if we just cannot go about detecting it in the visible or the infrared radiation, because the sky is a large background of these radiations. So if you go about detecting it in UV, then you can get a clear signature, and you can go about detecting missiles in a fraction of second, and then you activate your anti-missile technology to destroy the oncoming missile. So it has a very strategic importance, and we collaborated with uh, a lot of defense centers in India to work with them and develop this technology for them. Another application of these detectors in the deep ultraviolet is UV astronomy. Uh, so as you go deeper in the ultraviolet, you get to see more features of extraterrestrial objects, such as the sun here. So this is UV image of the sun taken 2 years apart that clearly shows an increasing solar activity, and especially in these areas where 2 years before the activity wasn't as significant. So to resolve such features, we need to enable deep ultraviolet photo detection, which was a part of my PhD, and we worked with ISRO to develop some technology for them. And here in the US, I work with NASA to develop this technology, and which is expected to fly out in the next couple of years for astronomical imaging. Another application of these detectors is in ultraviolet A and B. So this graph shows the increasing number of skin cancer cases in the US for 40 years from 1975 to 2014, and we see almost twofold increase in the skin cancer. So if we try to understand what radiations is the human skin most sensitive to, then we first look at how the sunlight spectrum behaves. So as expected, as we go down in wavelength, the radiance goes down, which means that we have much more intensity above 340 nanometers. But this is where your skin is not very sensitive to these radiations. So these do not give us a skin burn. But as you move lower in wavelengths, that's when you are moving higher in the energy of each photon. That's when your skin is very sensitive to the radiation. And if we now merge these two plots, then we understand that at about 310 nanometers, the skin is most susceptible to such wavelengths. So we need wearable UV sensors that can detect such radiations, and they can easily integrate with our mobile phones and suggest us that, okay, you are witnessing a harsh day and better put on your sunscreen, or better move indoors, because if you are out there in the sun, then you would be susceptible to a lot of damage. So this is where wearable UV sensor technology also is moving quite fast, and we have already started seeing features in some cell phones that have these sensors as a part of system on a chip. So if you look at the requirements of such ultraviolet detectors, so if you look at the UV astronomy based spectrometer that was used to image this image of sun by NASA, then we see that most of the weight consists of the battery that is needed to power such a big module. And then we need filters to filter out all the unwanted radiations. So the detector and focusing optics actually constitutes a very small fraction of this pie. So gallium nitride technology enables us to avoid the blue and orange pies here. We can enable um, like intrinsically blind self-powered detectors with a very low background noise, because remember, these detectors are based out of high bandgap materials that naturally filter all the visible and infrared radiation. So you really don't need a filter assembly because these materials act as natural filters. We can make them self-powered by enabling internal field in these materials. So you can go about detecting at no applied bias. You would still get a significant photocurrent in the circuit if you design the detectors properly. Uh, and these detectors also enable high quantum efficiency. So by high quantum efficiency, I mean the efficiency with which we are converting the optical energy into electrical energy. For instance, if you were to have 100 incident photons in your semiconductor, then you would want all the 100 photons to be converted into electrons and holes that now you can collect at the electrodes in your photodetectors. So that would be termed as 100% efficiency. But as no material is perfect, you always lose out on this efficiency. But as I'll be showing in the later slides, I and the previous speaker, we worked as a team, and we could enable world record uh, detectors with 92% efficiency at zero bias operation. So in optoelectronics, these materials also enable a range of light emitting diodes and lasers. So white light emitting diodes are something that we saw in the indium gallium nitride material with wavelengths about here. But aluminum gallium nitride enables ultraviolet A, ultraviolet B, and ultraviolet C radiations. And depending on the wavelengths, it enables a range of applications such as lithography, sensing, and as a light source at lower wavelengths. At intermediate wavelengths, which is UVB, these are exceptionally useful for medical treatment such as phototherapy. In UVC, these are very important for purification, sterilization. So this is very important in this day and age because UVC radiations can effectively kill the COVID virus. Uh, and it has been many commercial devices now have been enabled on this technology uh, to sterilize a particular room or particular equipment against COVID viruses and other bacteria as well. And UVC radiations, since they are free of solar background, can now enable a covert non-line of sight communication technologies as well. So again, as a function of wavelength and as a function of light output power, you have a myriad of applications for the light emitting diodes and lasers. Uh, based out of aluminum gallium nitride. And moving forward, we are going to see a lot of these applications getting traction and finally getting out there in the market. All right. So to understand how what makes it really difficult for these light emitting diodes to work at ultraviolet wavelengths, we need to understand how these work. So this is a simple schematic of how a light emitting diode works. So in a light emitting diode, we have N-type material. Remember, I talked about what makes an N-type material, which has excess electrons. Um, we also have a p-type material. So we use this n-type and p-type materials to inject electrons and holes to layers known as quantum wells that constitute lower band gaps. So now the idea is that you make the electrons and holes overlap such that uh, they create a photon corresponding to the band gap of the quantum well. So that's how you convert electrical energy that you use to inject electrical carriers into optical energy. And that's how a light emitting diode works. So the external quantum efficiency of a light emitting diode depends on the internal quantum efficiency. So that goes on to say that, okay, if you inject so many carriers in the active layer, how many carriers are actually working towards generating the light, and how many carriers are getting absorbed in the material due to the defects. So this is where the defects come into play, and these defects govern a lot uh, uh, of how high of quantum efficiency you can enable in these materials. What also comes into play is something known as light extraction efficiency. Since you are extracting light out of the semiconductor into a thinner medium such as air, since these two have very different refractive indices, uh, you lose out a lot of light because you deviate some fraction of light away from the focusing optics. So these two majorly limit the efficiency of these detectors. So if you look at the commercial light emitting diode, and if you go about looking at the cross section of these quantum wells, which are the active layers in these materials, then you realize that these are full of these one-dimensional defects. Remember, I talked about dislocations, one-dimensional defects that one material can have. And these materials are actually full of dislocations with such a large density. We have 10 to the 8 dislocation defects per centimeter square. But these materials magically work despite the fact that you have so many dislocations. And the physics behind it was only resolved a couple of years back, and it was a mystery to understand how these light emitting diodes work so efficiently. By efficiently, I mean that if you look at 400 nanometers, then the efficiency is about 80%. But then if you go down to larger wavelengths, then you see that the efficiency quickly drops. So this is for nitride-based LEDs. And then the phosphide-based LEDs can enable much better efficiencies at such low wavelengths. But there is a gap which is called the green gap, because for wavelengths corresponding to green, we haven't been able to generate light emitting diodes that are efficient enough. So this is called a green gap, and many groups are working towards enabling this technology, but very few have seen success so far. So this remains an active area of research. Now, if you go to the lower wavelength side, so we start from UVA to UVB to UVC, and we see that the efficiency droops down significantly. So you start with 80% efficiency. So again, by efficiency, I mean that from the 100 carriers that injected into the device, 80% of them produce light. So which is good enough. So which goes on to say that you are losing out very few carriers to generating heat, and you use most of the carriers to produce light. This is the reason why if you touch an LED bulb, it's always cold. LED bulb never gets hot because it's very efficient. But if you were to touch a CFL bulb, which is chlorofluoroluminescence lamp, or a regular tungsten filament bulb, then these bulbs get very hot. And the reason why they get hot is because most of the electrical energy is now getting converted into heat energy rather than optical energy, which is light. So that's the reason why the LEDs that most of you have in your houses run very cold or run at room temperature. But what happens as you go deeper in the ultraviolet is that the efficiency droops down to single digit or even lower than 1% at deeper ultraviolet wavelengths. And this is a big bottleneck for the commercialization of these LEDs, and it's also a billion-dollar market out there. But the existing technology is way too uh, is way too back in terms of commercialization. So I think for commercialization, we would at least need efficiency of 20 or 30% to get it out in the market and get the cost parity that one desires. So this is an active area of research that I also currently work on, and we have been working towards this day in and day out. And we see light at the end of the tunnel, but I think it will need another 5 to 10 years to get to the technology where we can have these available commercially, and these would be efficient enough for its use. So again, trying to understand why we have less efficient UV LEDs. Remember, I talked about how we, let's say, uh, when we have LED connected to the wall plug, let's say we start with 100%. Now, some of the energy is lost in the electrical circuit that drives your LEDs. So we call it the electrical efficiency. For indium gallium nitride based blue LEDs, we lose only about 10% in this conversion. Remember that here you have to step down from the 230 volts that comes to your socket to about 10 volts or 5 volts that the LED commands. And during this step down process of, and also from converting from the AC that you get to the DC that the bulb needs, you lose out about 10%. But in aluminum gallium nitride deep UV LEDs, you lose out even more, about 30% in just the electrical circuit. Then we talked about internal quantum efficiency, and that depends on the defects in the multi-quantum well, which is active region in these LEDs. And these can be very low if you have a lot of defects in the material. Blue LEDs magically work very well despite having a lot of dislocations, but Algan LEDs do not work well with dislocations. So the internal quantum efficiency is low for these, and that's why the graph goes down further to about 40%. And then we have a lot of issues with light extraction. As you can see in the schematic, the light gets emitted in all directions. So you need a good focusing optics to now focus all of this light and then emit out of the bulb. But in this process, we lose out on a lot of light as well. So that's why in PPUV LEDs, you end up with efficiencies as low as 10%. And then the issues are also based off uh, uh, difficulty in producing n-type material and the p-type material. Remember, n-type material is excess electrons, and p-type material is excess holes. And since these materials have a large band gap, it becomes very difficult to make these materials p-type and n-type by traditional doping methods. And because of this, we have a lot of loss due to the poor contacts to these layers. And all of these losses now come into factoring the efficiency down from the starting 100% and the wall plug to only about 5 or 10% at the end. So I talked about a lot of applications. I think I'm going to talk more about 10 to 15 minutes and discuss how we go about depositing these materials. So I really focused on the application so far, but now let's look at practical end of things and see how we deposit these films. So in IIC, we did it using this reactor. This is called metal organic chemical vapor deposition. So it's ironic that the films that we are growing are few nanometers in thickness, which is very small number. But to have a controlled deposition and to control the defects in these materials at parts per million size range, you need a reactor which is as big as this. And this reactor would cost one about 10 crores of rupees, and the maintenance of such reactors is about 1 crore rupees a year. Uh, and this is only a research grade reactor. So the commercial reactors that the previous speaker showed in one of the slides, those are 5 times bigger than these reactors, and those would cost about 25 to 30 crores per reactor. So it's very expensive technology just to research on, and that's the reason why India has only 3 or 4 of such reactors, and it's very difficult to get a funding for an entire new reactor since the quantum of money is in tens of crores. So this really enables us to grow complex structures like the ones shown here. Although the uh, film thicknesses are only nanometers in size, but you still need such a large reactor to control the deposition. And if you go about opening one of these cabinets, gas cabinets, then you see a trail of lines. So these are gas lines through which we pump the precursors and make them react in. So this is the main reactor, and I would like to highlight here is that the gases that we have to deal with in such reactions are extremely pyrophoric and toxic. So if there is a leak, uh, the the body would not know whether to die of the toxicity or whether to die of the fire that is produced when these gases are exposed to the environment. So it's very dangerous if we have leak, and that's why we have a series of leak detectors hooked up to the reactor. If these detect any leak, then it just shuts down all the gas lines in a fraction of second, and that's how you can go about doing such experiments in a safe manner. But it's a very harmful set of gases that we have to deal with to synthesize these semiconductors. And the reactor operates at elevated temperatures such as 1200 or 1300 degrees Celsius, which is a crazy high temperature by any normal standard. But we have to go to such high temperatures to synthesize these semiconductor materials and let the chemistry do its trick. So eventually we end up with very nice looking materials if we optimize all the parameters involved. For instance, this is the aluminum nitride and sapphire interface. If you look at it in an electron microscope, you can resolve atomic columns. So you can see all these lines that you see, or all these dots that you see, are actually atomic columns. You can look at the length scale here, which is 5 nanometers. So the inter dot distance is like 5 angstroms, which is zero point 0.5 nanometer, and that's about the bond length of these materials. And you can nicely resolve all these atomic columns in this powerful electron microscope. Again, this microscope itself would cost about 9 to 12 crores, depending on the functionalities you bring along. So it's very expensive field overall to research on, and that's why the center at the sense actually boasts a range of facilities, and the budget for all the facilities is about 7 to 800 crores of rupees uh, in just enabling this one center with an annual maintenance cost of 25 to 30 crores. Um, so so our reactor was in a clean room, and that's why you see me in a bunny suit, like like an astronaut, because we have to. Once we are in clean environment, humans are the potent source of particles, and that's why you have to gown up, and that's how you work in the clean room. And you have to for a typical growth run, you spend hours doing one growth run. By growth run, I mean one synthesis, and you spend hours doing that wearing a bunny suit. So it's an exciting experience. uh, so here I had designed this presentation to show you a lot of experimental part of my talk, but I think I'm already exceeding the 1 hour that was allotted to me. So I'm going to just skip the slides and go to my conclusion. All right. I will pause here just for a bit, where I would like to highlight the key result that me and the previous speaker could achieve. Here you have this complicated architecture of photodetector, but what we could achieve was that even at zero applied bias, we could get a light to dark current ratio of 10 to the 8, which means that if you do not have any radiation on your detector, you record femtoamperes of current, but as soon as you shine light, UV light, you measure microamperes of current, making this one of the most sensitive detectors which has ever been developed. And the efficiency was found to be 92% for these detectors, which is the world record for such photodetectors. And all of this was only possible by a careful optimization of materials at atomic scales, all those defects that I talked about. Only when you take care of these defects and try to understand how these defects uh, mm, uh, impact your device performance, can you make very clean material, and that's how you can enable such high efficiency. So this was one of the biggest success that we could work on during our PhD. Uh, Again, we made amazing results, but in the interest of time, I'll have to skip through all these results. But just to summarize, I talked about a lot of power electronic applications that these materials enable, uh, and a lot of optoelectronic applications. So we saw that gallium nitride power electronics is going to be a multi-billion market in 2030, where we're going to see a lot of uh, uh, proliferation in the consumer market, in the automotive market, in the industrial market as well. Whereas the RF market is already in billions of dollars, and it's expected to expand to satellite communication, and the 5G infrastructure is going to grow further. We're going to see a lot of 5G in India in only a couple of years. We have already started receiving 5G cell phones, but now we are also going to see a lot of 5G towers, and the base stations in these towers would be made out of gallium nitride. Uh, and we are going to see a continual use in defense sector for applications that I discussed in my presentation. And then we are possibly going to see gallium nitride in our mobile phones as well. So let's look at what the future looks like beyond gallium nitride. So we spoke about how gallium nitride is more efficient than silicon and silicon carbide technologies because of its higher critical field strength and mobility. But now we have development of aluminum nitride that enables much higher critical field. So you can see that the critical field is 5 times higher than gallium nitride. And in the figure of merit, the field goes as cube of the electric field, and we can quickly understand as to how promising aluminum nitride is going to be. And same goes for diamond, that not only has a good breakdown field, but also high mobility. And we're going to see a lot of power electronics based out of gallium nitride, aluminum nitride, and diamond in the future. So I hope that that sets a tone for the theme of this FDP to talk about future transitions. And I believe that we are going to see a lot of aluminum nitride based power electronics in the near future. So thank you for your time, and I'll be happy to take questions. And if I'm not able to take all the questions today, please feel free to touch base with me over my email, and I'll be happy to revert back to your emails in a day or two. So thanks again for your time, and I'll be happy to take questions.
Thank you, sir. I would now like to take questions from participants. Sir, first question is, can you please share your thoughts on the importance of interdisciplinary research in this day and age?
Yes, I think it's a very good question and very pertinent for this day and age. I think it's imperative for everyone to be doing cross-disciplinary research. Um, I believe that's the way to go moving forward. For instance, in my case, if I would have been only a material scientist, then I wouldn't have been able to broaden my perspectives to the ones that I have right now and appreciate things from both ends of things. For example, material scientists are experts at understanding how the material behaves at different length scales and so on, but they still struggle to understand how the material is going to translate when you make devices on top of it. And on the other hand, you have electronics engineers that are experts in understanding how the device works electrically, but they struggle to understand how the performance is coupled to the material. So there is this gap that I really liked to bridge during my PhD. And I believe that such gaps exist between various disciplines. But to make the best of both disciplines, to put the knowledge to the best use, one really needs to work on the intersection of different fields. And I was very happy to collaborate with a range of PhD students and faculties at Sense coming from varied backgrounds. So I'll just give one example. For instance, one of our professors, he is an aerospace engineer, but he works on DNA sensing and biosensing now. So you can understand how big a pivotal shift that is from aerospace to bioengineering. And one of our ex chairmen of the center, he is a civil engineer by training, but he went on to do a master's in mechanical and then a PhD in mathematics. And now he tries to work on mechanobiology. So people really make these pivotal transitions in their research career, and they still outperform most of the scientists that really stick to one single domain. So I think it's an imperative thing to do in this day and age, and I would really encourage everyone to give this a good thought.
Next question is, can you tell about INUP at IISc?
All right. So I think it's a very interesting program that is offered by Center. It stands for Indian Nano Electronics Users Program. It has a website of its own that keeps uh, updating every day. So I think visiting the website would be the best idea to get acquainted with the INUP program. And I think the frequency of the program is about once in 2 months or once in 3 months. And their professors and students from any Indian institution can apply. So they have to, I think, give a brief research proposal or at least some background on why this program is going to benefit them. And that's how, from a pool of candidates, they go about selecting only a certain number. And then they spend time at the center learning about all the equipments involved and even try to work on their own projects. So I think it's a very good program for anyone in electronics uh, and related fields, even electrical engineering, materials engineering, mechanical engineering. Like I pointed out, in this day and age, it's things are not to be meant for uh, strictly confining your research to one domain, but nanotechnology is the best example that demonstrates how cross-disciplinary research is the way to go moving forward. So INUP program teaches that as well. So I think I would highly encourage you all to either attend it or send your students or recommend it to your students to attend in the near future.
Yes, sir. So next question is, what advice would you give to the faculty participants on how to initiate intra-university and inter-university collaborations?
I think this is another very nice question, and which is very important for all the faculty members attending the FDP. I think the way you can go about is first that you should have a thorough literature survey of your research area, and then you need to identify uh, who is aligning nicely with your research domain. And the way you can go about is start by pushing some emails to the concerned scientist or professor, and uh, writing a brief but yet informative email, making them realize that you really uh, went out of your way to read some of their papers, and then you have specific feedback on their papers and the way you think the research can be made better. I think that that can be one of the approaches of collaborating in intra-university level. In inter-university, it's much easier. You can just drop by their office and discuss it in person. Um, uh, but I think in intra-university, that's the way you can go about at individual level. When it comes to management level and when there are more MOUs signed between different universities, then things get more streamlined. But I believe that most of the inter-university collaborations still stem at individual level. And that's what paves the way for many MOUs to be signed between the two universities. Uh, so I think that answers the question.
Yes, sir. Sir, one more question from participant. How many years it would take for silicon to gallium nitride semiconductor transformation in all equipment?
That's another very interesting question. So the answer is not straightforward. For different technologies, the time frame is going to be very different. But replacing silicon is going to be a Herculean task for gallium nitride because the industry is all optimized for silicon. Silicon is available over large sizes, like 12-inch diameter wafers are routinely available, and all the systems have been optimized to work at such large wafer scales. Whereas gallium nitride is still only at 8-inch technology node. So it will take some time, but I would say that in power electronics, we are already seeing a lot of gallium nitride devices that are replacing silicon. So in gallium nitride, it's already in the transition so although it's like poised to replace it all, uh, but I think it will take like another 10 years for replacement of all the power devices. And the RF devices are also coming into play, as you can make out from the huge billion-dollar market that RF devices have. So I think in next 10 years, you should also see a lot of gallium nitride RF market. And in optoelectronics, although these are efficient, much more efficient than silicon, still I think there are many challenges involved in packaging and reliability that hasn't been studied yet. So in optoelectronics, I would guess it would take longer for the technologies to come into market.
Yes, thank you, sir. Yes, any more questions from participants? Thank you so much, sir. Your research work is very promising and certainly moving toward the state of art. It seems to be encompassing a range of engineering applications using gallium nitride. You have explained, very well explained, many applications of semiconductor materials and also focus on the research domain, various research domains like MEMS, microfluidics, nanobiotechnology, microelectronics, photonics, and so on. Thank you, sir, for
Thank
your
you.
valuable inputs. Also, we are extremely grateful that in spite of this time difference, you have delivered this session according to our schedule. Now I request Dr. Rajesh Thakre, sir, and Mahesh Pawar, sir, to present a memento to Dr. Kantiwar.
First of all, thanks so much for this opportunity again. I thank all the organizers for this wonderful opportunity. It's wonderful to be here and addressing this FDP. And I have attended other sessions as well. And I must congratulate you all, the organizing committee members, to be doing a fantastic job at it. I enjoyed most of the sessions that I could attend. And I think YCC should organize many more such events and uh, uh, make its image even better than what it is today. So,
Sir, I request you to accept a token of gratitude on behalf of organizing team and Yashwantrao Chauhan College of Engineering, Nagpur, for sparing your valuable time and guiding us.
thank you so much. The pleasure was all mine.
So all the participants are requested to turn on your camera for photograph. Done. So one more. Yes. Done.
All right. So thank you so much again. Thanks everyone for attending this session and have a wonderful day ahead.
Thank you, sir, for this nice session. Participants, dear participants, you have your next session at 3:30 p.m. Next speaker is Dr. Chetan Radekar, Massachusetts Institute of Technology, Cambridge, USA. Thank you all.